Okay, in this video I'm going to talk about the derivative rules, which you'll be overjoyed to hear about because so far the method for finding derivatives is by taking using the definition derivative, which involves a limit process and generally a lot of algebra and half a page of work just to get a derivative. So what now we're moving into the kind of rule and heavy algebra section of the class because we're going to be basically, some people call these shortcuts because in comparison to the definition derivative method they are very short. But they basically they're a set of rules that the mathematical geniuses that come before us have figured out, and so they've put them down in a set of rules so that we can learn them fairly easily, and we can greatly speed up our ability to take derivatives. So now the first thing, and this is kind of a unique way that I teach it. The first thing that you need to learn in the rules is something called the chain rule, and that's right at the top of this sheet. So this sheet is in your Canvas. In the week 3 module down at the bottom it says, the chain rule is the basic idea that if you have a function within a function, if you remember from pre-cal, we have composite functions. So if you have, for example, like sine of x squared, you could think of that as a function within a function. Have to take the derivative of the outside first, and then multiply that by the derivative of the inside, and just keep going until you get all the different layers. So that's a rule that applies to every derivative we do, and we'll talk about that as we go. But the other thing we need to talk about here is the notation. This is what is called Leibniz notation, and I think it's very handy because it reminds us what we're doing. So when you see something like this, let me get that out of there, this d over dx, so this means the derivative of something with respect to x. Now, anytime you're taking a derivative, remember a derivative is a rate of change, so you're comparing something changing on top to something else changing. And at the beginning, we've talked about dy dx, which is kind of the same thing as slope. That's what you've heard a lot about because that's the change in y versus the change in x. But we've also talked about change in distance compared to change in time. That would be velocity. We've also talked about change in velocity compared to change in time. That would be acceleration. So a derivative is always a rate of change, which means we're always comparing a change in something to change in something else. So what this notation right here means is I'm comparing the change in the u function in comparison to the change in the x variable. Okay? So notice that this is a function of t. So this is saying if you take the derivative of a function of t, you would take the derivative of u with respect to x, then multiply that by the derivative of t with respect to x, and then multiply that by the derivative of x with respect to x. And of course, notice this is just equal to 1, so that would just disappear, so your derivative would just be this part here. So that's the idea of the chain rule. Again, that might have just went right over some of your heads, but it'll make more sense as we go. So then, as we go down here, we'll look at these other the other rules. So notice here, we're taking the derivative of a with respect to x. So now a, we need a quick little lesson here on variables. There's kind of an unwritten rule about variables that in general, when we're talking about graphing, we use x and y. That's pretty standard. And you may have noticed this when you talk about trigonometry or you measure an angle. Often we use Greek letters like alpha and beta and theta. But also, and this is something maybe you haven't picked up on, often when we're talking about a constant number, so a number that's constant, we just don't know what it is yet. So it's not really a variable in the sense it's varying, like x. You can replace x with a bunch of different numbers possibly. But it's a constant that we don't know what it is. Often we'll represent that with an a, b, or a c. So that's what this is supposed to signify. When I'm taking the derivative of a constant, it's 0. So, like for example, let's say your function is f of x equals 5. So if I was to take the derivative of that, it would just be 0. Now hopefully that makes sense to you, because what we're saying is we're taking the change in 5 in comparison to the change in x. Well, 5 is not changing, so it doesn't really matter how x is changing. When we compare the change in 5 to change in x, we'd have the change in 5 is 0. So as x changes, 5 stays the same, right? So if you're looking at the graph of that, right, f of x equals 5 would be 1, 2, 3, 4, 5. It's a horizontal line, and once again you can see that as x is changing, as I'm plugging in different numbers for x, the y is always 5, so there's no change in the y. So that's that. This is kind of a common sense thing here. The derivative of a constant number is 0. Okay, so that's the first rule. The second rule, this says, well, what if you have a constant number times some variable? So let's say, for example, we have f of x equals 3x. Now again, if we look at the graph of that thing, whoops, I missed the the origin. It would look something like this, right? It'd be a line with a slope of 3 and a y-intercept of 0. So what this is saying is, if you take the derivative of that, you will just get the derivative. You will just get the constant, the 3, times the derivative of the other stuff. So, for example, in this case, this would be the derivative of this, which I think I've shown this before. That means derivative. The derivative of this would be 3 times dx dx, which of course is just 1. So this would just be 3. But if f of x is equal to, say, 3 sine x, well, then the derivative of that would be equal to 3 times the derivative of sine x. Right? So that's what that means there. That in other words, the a, or the constant, just kind of goes along for the ride. So you can see that this du dx would be this part in the case of this function. Okay? So when you have a number multiplied out front, it just stays there, and you take the derivative of the rest of the stuff. It's just being multiplied by. That's the second rule. The third rule says if you're trying to add two different things together and take the derivative of both of them, well, you can just take the derivative of them separately and then add them together. So if I had a function, for example, that's equal to sine x plus cosine x, then the derivative of that would be the derivative of sine x plus the derivative of cosine x, which we'll have to go down here to see what that is. But for right now, I'm just showing you that this rule is just telling you that you can take the derivative separately. Okay? Okay. Now, here's the first rule that's really that's not just kind of an obvious one. This is called the power rule. So this is saying if I have something raised to a power, and once again, n is often a constant number, that it's usually the counting numbers like 1, 2, 3, 4, 5. So this is saying that I've got something raised to a power. So if I take the derivative of that, what happens is I multiply out front by the power, and notice the power drops 1, the u stays the same, and then I multiply by the derivative of that thing. So for example, if I have f of x is equal to x cubed, well, the derivative of that would be 3 times x squared, because I multiply by 3, drop the power 1, times the derivative of x, which in this case would be 1, so it would really just be 3x squared. However, if I have f of x equals, let's say, I don't know, tangent x cubed. Well, once again, the derivative would be, and this is where that chain rule comes in, the derivative would be multiplied out by 3. Notice the tangent x stays the same because the u stays the same here, right? The power drops to 2, and then I'd have to multiply that by the derivative of tan x. Okay? So what we're focused on right now is just getting the rules down and not so worrying so much about these more complex ones. So what you're going to see initially is just some real basic questions like what's the derivative of, say, x cubed plus 3x minus 5. Okay? So notice we're going to use this rule, and this rule, and that rule to answer that question, right? Because this is telling me I can just break them up into pieces and take the derivative of each one, so that's helpful. So I take the derivative of, if I take the derivative of x cubed, that's just this rule here. That would be 3x squared times dx dx, which is just 1. If I take the derivative of this one, that would be this rule here. So that would just be plus 3 times the derivative of x, which is just 1. And then if I take the derivative of negative 5, that would be like this one here, which is just 0, so I don't bother writing it. So that would be my derivative, 3x squared plus 3. So the derivative of x cubed plus 3x minus 5 would be 3x squared plus 3. Okay? So that's the first, that one is probably used more than any other rule because there's tons of things that we use, involve powers on a lot of different functions, so that one comes up a lot. So anytime you have a power, you're going to apply the power rule, right? So now we get into the more the more rare ones, I guess. I wouldn't want to say rare because we use them, but they're not as common as the power rule. So this one is the exponential rule. So this says if I have notice again, this a is representing a number and the u is something involving a variable. So if my function is, for example, 5 to the x power, that's 5 to the x, right? So this is telling me that the derivative, so what does that say? Well, first of all, I'd have to multiply out front by the natural log of whatever a is. So in this case, that would be natural log of 5. That's my first move. I'm multiplying by natural log of 5. But notice that this guy is still there. So basically, I'm taking what I had before and multiplying it by the natural log of the base. So that would be 5 to the x. And then, of course, I'd have to, the chain rule would tell me I'd have to take the derivative of x. In this case, it would be dx dx, which, of course, is just 1, so I wouldn't bother writing that. Okay? And that would be my derivative. Okay, to just give it another example, let's say g of x is equal to 7 to the sine x power. So once again, the derivative, first of all, is going to be the natural log of 7. Got to multiply that out front. And then I have a 7 to the sine x, because notice that whole thing is still there. In this case, sine x is the u, right? And then I'd have to follow up by multiplying by the derivative of whatever that u was. So that would be the derivative of sine x over dx. Right? And since we don't know what the derivative of sine x over dx is, we'll just leave it like that. Just so you can see how this would happen. Notice, let's hop down here real quick. So this one here, right here, tells me what the derivative of sine x is. Apparently it's cosine x, right? So I could then replace this with just a cosine x, because that's what the derivative of sine x is, times the derivative of x, which of course is just 1, so I don't bother writing it. So that would be the complete derivative of that guy up there. Okay? And I'm going to do one more, then I'm going to kind of turn you loose on these ideas. So the last one is the log rule. So this says, for example, if f of x is equal to log base 7 of x, and I want to take the derivative of that. So the derivative of that would be, well, what does this say? This says, notice that u is the thing that I'm taking the log of, right? So notice this, first of all, I've got a 1 on top. I have the u on the bottom, so in this case that would be x. But then I also have this little natural log of a. Well, a in this case is the base of the logarithm, so that would be natural log of 7. So I'm multiplying the bottom by natural log of 7. And of course I'd multiply by the derivative of whatever u was. Well, in this case, u was x. So that would be dx dx, so it'd just be 1, so I don't bother writing it. Because 1 times this would just be itself. Okay? So that's the first 6. If you go to the practice sheet, there'll be some examples of all of these, and you should be able to work your way through it. There will also be some trig questions on there. This just says the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared, etc. So at this point, you should be able to use all of these rules. Definitely there's some confusion about them, talk to me. Don't worry about the rules down below here. Okay, so go practice and have some fun.